This is part of our video series on human-centered evaluations for NLP explanations. Check out the link for more resources. You're currently here.
Once we've collected a data set of human explanations, the next question is how to use them as a gold standard for model explanations. It's easier to do so with rationale-style explanations where evaluation is basically just the same as any sequence classification task. However, there are still a few nuances here involving properties of both the human-annotated rationales and the model-generated rationales. So just a reminder, we're trying to evaluate the model-generated rationale on the right relative to the human-annotated rationale on the left in this example. In the simplest scenario, both the human rationale and the model rationale consist of one binary value per token. In this case, we can simply calculate measures of binary token-wise agreement, such as precision, recall, and F1. However, most explanation methods output continuous rather than discrete values. In cases where these values are on a consistent scale, such as with certain attention mechanisms, we can either choose to apply a sensible threshold for binarization and then apply binary metrics, or we can normalize to 0 and 1 and calculate continuous metrics like mean squared or mean absolute error. One common scenario is that model rationales are generated by softmaxing across the length of the input. An example is if we look at the internal attention weights of a transformer-based model, which are produced by this type of operation. This is actually a tricky situation because it coerces variable density rationales across variable length sequences to a consistent sum, putting them on different scales from both the human-annotated rationale and from each other. A common approach here is to choose the top k tokens from each model rationale and then compare them to the top k tokens from each human rationale. But there isn't really a good way to choose this k. Setting it to the length of each individual human rationale requires too much information, and setting it to some global value discounts the fact that different rationales have different numbers of causal tokens. A better approach, although not one that I've actually seen in the literature, is to treat the softmax values as a ranking over the tokens and then apply measures of rank agreement such as average precision. Another common scenario is where the model rationales are on some arbitrary scale. Saliency methods will do this, as will some perturbation methods like Lime. Practically speaking, this is the same scenario as a softmax rationale, and the approaches for dealing with it are the same. Top K is typical, but ranking metrics are probably more appropriate. Sometimes we want to evaluate token-level rationales at the level of spans rather than individual tokens, whether it be contiguous human rationale spans, sentences, or sentence phrases. The simplest approach here is to just average or otherwise aggregate the model rationales across the desired spans, and then define a criteria for whether the model matched that span. In the above example, I'm simply binarizing at 0.5, meaning that if the model caught 50% of a given human rationale span, it counts as a match. Finally, in cases with multiple human explanation annotators, there is going to be a certain amount of uncertainty associated with each human rationale. One way to deal with this is to simply weight each human rationale token by how close it was to being unanimous, and then apply this weight to whatever token-wise metrics you happen to be using. All of the metrics discussed above are available in the scikit-learn metrics module, and almost all of them have a sample weights optional argument for dealing with uncertainty in the ground truth. Evaluating free text explanations is much harder, just like evaluating natural language generation is hard generally. A number of simple methods have been proposed over the years for the general task of natural language evaluation. This recent survey by Cristina Garbacia has a very nice overview. We can revisit our running example here, where we have two annotated natural language explanations, one of which is pretty good, and the other of which is pretty bad. And then we have this explanation generated by GPT-3, which is arguably better than either human explanation. So the question is, how can we use these human-generated free text explanations to evaluate the one generated by GPT-3? One very common metric is Rouge, which simply measures n-gram overlap between the generated text and the reference text. This was originally designed to evaluate summarization algorithms, but is common across the NLG literature these days. Another very common metric is BLUE, which computes clipped n-gram precision scores between the generated text and one or more reference texts. Blue was created for evaluating translation models and is also all over the place in the NLG literature. A more recent metric is word movers distance, which involves performing an alignment between the tokens in the generated versus the reference text, and then calculating the average cosine distance between the word embeddings of the two texts. Finally, a common non-similarity-based method is perplexity, which calculates the likelihood of the model's output, effectively measuring how certain it is of its own generated text. And then the variant of this idea, which makes use of the reference texts, is so-called reverse perplexity, where a second language model is trained on the output from the first, and then the likelihood of the reference texts is calculated relative to this model. To conclude, proxy evaluations between human and model explanations tend to assess similarity between the two. Doing this with rationales is relatively easy. It just takes some informed decision-making about how to scale or threshold the model rationale and what metric to use. Free text explanations are harder. Natural language generation is hard to evaluate as it is, and evaluating free text explanations is made more difficult by ambiguity over the purpose of these explanations. What are they supposed to do? Informationally speaking, is trying to match them to human-annotated explanations even a valid objective? And that really begs the main question here, which applies to both types of explanation. Should model explanations be similar to human explanations? Or is that a fundamentally flat objective, making the whole idea of proxy evaluations kind of useless in this context?
This video isn't the end. You're currently here. If you're lost, click on the link below for source code, slides, and other resources.